The universe is an endless expanse of mystery, a cosmic tapestry woven with secrets we've only just begun to unravel. Among its countless stars and galaxies lie worlds so strange, so utterly bizarre, they seem ripped straight from the pages of science fiction. Picture a planet where it rains glass sideways, or a world so dense a teaspoon of its material would weigh as much as an elephant. These aren't figments of imagination, they're real places, discovered by astronomers peering into the depths of space, each one defying everything we thought we knew about how planets form and behave. For centuries, we believed our solar system was the blueprint for how planets worked, but the more we explore, the more we realize just how wrong we were. The universe delights in throwing curveballs, crafting worlds that challenge the very laws of physics. Take, for instance, a planet so hot its atmosphere is vaporized metal, or another that orbits its star backward, breaking every rule of celestial mechanics. These aren't just oddities, they're cosmic puzzles, each one offering clues about the incredible diversity of planetary systems beyond our own. And the discoveries keep coming faster than ever before, thanks to cutting-edge telescopes and the tireless curiosity of scientists determined to map the unimaginable. Today, we're diving into 25 of the strangest planets ever found, places where the familiar rules of day and night, gravity, and even chemistry don't apply. From worlds darker than coal to planets with not one, but three suns blazing in their skies, each of these discoveries rewrites what's possible. Some are so extreme they shouldn't exist, yet there they are, lurking in the data, waiting to astonish us. So buckle up, because this journey isn't just about exploring distant worlds. It's about stretching the limits of our understanding, one mind-bending planet at a time. If you think diamonds are rare and precious here on Earth, wait until you hear about 55 Cancri E, a planet that might just be the ultimate cosmic jewelry box. This super-Earth, located about 40 light-years away, isn't just sprinkled with diamonds. Scientists believe a staggering third of its entire mass could be compressed into crystalline carbon, forged under pressures so intense they turn ordinary matter into glittering celestial treasure. But don't expect to take a leisurely stroll across its surface. 55 Cancri E orbits so close to its host star that a single year there lasts just 18 hours. That blistering proximity means surface temperatures soar beyond 2,000 degrees Celsius, hot enough to melt steel and vaporize rock. Imagine a world where the ground beneath your feet isn't just scorching, but potentially studded with diamond formations, all while being bathed in the relentless fury of its sun. What makes this planet even stranger is its composition. Unlike Earth, which is rich in oxygen and silicon, 55 Cancri E is packed with carbon. Under the crushing weight of its own gravity, that carbon could have crystallized into vast diamond layers, creating a landscape that's as deadly as it is dazzling. Some researchers even speculate that beneath its searing atmosphere, the planet might harbor a molten sea of liquid diamond, churning in perpetual superheated motion. Yet for all its allure, this diamond world is anything but habitable. Its atmosphere, if it even has one, would be a toxic mix of vaporized rock and ionized gases, more like a planetary forge than a gemstone paradise. And with tidal forces locking one side permanently facing its star, the planet's day side is a broiling wasteland, while the night side might still be hot enough to glow faintly from residual heat. 55 Cancri E challenges our assumptions about what planets can be. It's a reminder that the universe doesn't just create worlds, it engineers extremes where the familiar becomes foreign and the impossible turns out to be just another Tuesday in the cosmos. If 55 Cancri E is the universe's diamond-hard enigma, HTP-1b is its cosmic featherweight, a gas giant so absurdly light it defies every expectation. Imagine Jupiter, but stretched to nearly twice its size while somehow weighing half as much. This planet doesn't just float, it practically billows like a balloon caught in a stellar breeze. Astronomers call these worlds puffy planets, and HTP-1b is one of the most baffling examples ever found. What makes this giant so oddly inflated? The answer lies in its scorching orbit, just 1/20th the distance between Earth and the Sun. Bathed in relentless stellar radiation, HTP-1b's atmosphere has swollen to grotesque proportions, like a marshmallow left too long over a campfire. Heat pumps energy into its outer layers, causing them to puff outward while its core remains strangely lightweight, less like a traditional gas giant and more like a loosely packed cloud of hydrogen and helium. Some scientists speculate that internal heat left over from its formation might still be bubbling up, further stretching its already bloated atmosphere. But here's the real twist. HTP-1b shouldn't exist at all, at least not according to classic planet-forming models. Gas giants are supposed to condense from cold, dense disks of material in the outer reaches of a star system. Yet this planet orbits impossibly close to its sun, where temperatures should have prevented such a fragile structure from ever taking shape. One theory suggests it might have migrated inward after forming farther out, but even that doesn't fully explain its extreme fluffiness. Others propose that unknown chemical processes in its atmosphere, perhaps even exotic compounds absorbing and re-radiating heat, could be acting like a cosmic oven, keeping the planet perpetually inflated. The strangest part, HTP-1b isn't alone. Over a dozen similar hot Jupiters have been discovered, each with their own quirks, but none quite as exaggerated. These planets force us to rethink how gas giants evolve under extreme conditions, revealing that the universe has a flair for turning planetary science on its head. So next time you gaze at the night sky, remember, out there, worlds like HTP-1b are drifting like spectral giants, their secrets still waiting to be unraveled. While the universe dazzles us with glittering diamond worlds and improbably puffy gas giants, TRS-2b lurks in the shadows, a planet so dark it makes the blackest coal look blinding by comparison. Discovered in 2006, this distant gas giant holds a chilling distinction. It reflects less than 1% of the light that hits it, earning it the nickname the darkest planet ever found. If you could stand on its surface, if it even had one, you'd be immersed in an abyss so complete, it would feel less like night and more like staring into the void itself. What makes TRS-2b so unnervingly black? The answer lies in its atmosphere, a broiling soup of vaporized chemicals unlike anything in our solar system. Most hot Jupiters, bathed in the intense glare of their host stars, develop hazy, reflective layers that bounce some light back into space, not this world. Its air is packed with light-absorbing molecules like sodium and potassium, along with exotic compounds like gaseous titanium oxide, a substance so efficient at swallowing photons it turns the entire atmosphere into a cosmic black hole. Even stranger, the planet's scorching temperatures hovering around 980 degrees Celsius should theoretically make it glow faintly with heat radiation. Yet it doesn't, it just sits there, an inky silhouette against the fiery glow of its star. Scientists are still unraveling the mystery of why TRS-2b is quite this dark. Some speculate that its atmosphere might lack the reflective clouds found on other hot Jupiters, allowing light to plunge deep into its depths where it's absorbed and never seen again. Others wonder if unknown chemical reactions are at work, creating a perpetual shroud of light-devouring haze. Even its position plays a role. Orbiting just 5 million kilometers from its star, the planet is tidally locked, with one side forever facing the stellar inferno. That constant barrage of radiation might be stripping away any chance for reflective particles to form, leaving behind only a planet-sized blot of darkness. The eerie thing, TRS-2b should be visible. Its star, JC 03549012181, is nearly identical to our Sun, meaning the planet ought to gleam like Jupiter does in our own sky. Instead, it's nearly invisible, detectable only by the faintest dip in starlight as it passes in front of its sun. This isn't just a dark planet, it's a cosmic stealth fighter hiding in plain sight. Finding TRS-2b has forced astronomers to rethink how atmospheres behave under extreme conditions. It's a reminder that the universe has more tricks up its sleeve than we ever imagined, including painting entire worlds in shades darker than the void between stars. And if that wasn't unsettling enough, here's the kicker. TRS-2b might not be alone. New observations suggest there could be an entire family of these shadowy planets out there, each one waiting to vanish into the cosmic backdrop. So next time you gaze up at the night sky, remember somewhere in that sea of light, there are worlds so dark they're invisible to everything except our curiosity. In the cosmic ballet of strange planets, few performances are as bizarre as the duet between Kepler-36b and Kepler-36c, two worlds so different, yet locked in such an intimate orbital embrace they defy logic. Picture this, a rocky super-Earth and a gaseous mini-Neptune, separated by a mere 1.2 million miles, closer together than any other known planetary pair in the universe. To put that in perspective, that's less than 5 times the distance between Earth and the Moon, yet these two couldn't be more different if they tried. Kepler-36b, the inner planet, is a dense, scorched super-Earth about 1.5 times the size of our home world, with a surface likely littered with molten rock and searing lava flows. Its sibling, Kepler-36c, is a fluffy mini-Neptune nearly 4 times Earth size, wrapped in a thick, gaseous shroud of hydrogen and helium, a planet without a proper surface where any visitor would sink endlessly into its soupy atmosphere. Normally, two planets with such radically different compositions and densities wouldn't dream of orbiting this close. Gravity, chemistry, and simple physics should have torn them apart or sent them crashing into each other eons ago. Yet here they are, dancing around their star in a cosmic counterpoint that leaves astronomers scratching their heads. How do they manage this gravitational tightrope act? The answer lies in something called orbital resonance, a delicate celestial rhythm where their orbits sync up in a precise ratio, pulling and pushing each other just enough to maintain stability without catastrophe. Every 97 days, Kepler-36c completes exactly 7 orbits around its star, while Kepler-36b finishes 6. This mathematical harmony keeps their chaotic tug of war in check, like two dancers spinning just fast enough to avoid colliding. But don't let that harmony fool you. Their closeness creates gravitational fireworks. During their closest approaches, the planets stretch and squeeze each other with tidal forces so extreme they likely trigger planet-wide quakes on the rocky Kepler-36b and churn the atmosphere of its gassy twin into violent storms. Imagine standing on Kepler-36b's surface, if you could survive the 1,000-degree heat, and looking up to see Kepler-36c looming in the sky, appearing 20 times larger than our Moon. It would be an unnerving sight, a colossal, swirling neighbor so close you could almost reach out and touch it. The existence of this odd couple challenges everything we thought we knew about planetary formation. Conventional models suggest gas giants and rocky worlds should form in distinct regions of a star system, separated by vast distances. Yet Kepler-36b and c somehow ended up as next-door neighbors, a cosmic paradox that hints at hidden upheavals in their past. Did they form farther apart and migrate inward? Was their star system once home to other planets whose gravity nudged them into this precarious arrangement? Every answer only leads to more questions. What's certain is this: the Kepler-36 system is a reminder that the universe loves extremes. It's a place where the rules we take for granted bend and twist, where planets rewrite the script on what's possible. And somewhere out there, amid the infinite dark, these two mismatched worlds continue their endless dance, a gravitational oddity spinning silently in the void. If you thought sideways rain was strange, WASP-76b takes weather forecasts to a whole new level of terrifying. This ultra-hot Jupiter, located about 640 light-years away, doesn't just have storms, it has literal showers of molten iron. Imagine a world where the daytime sky isn't blue, but a blinding metallic haze, where the heat is so intense it rips metals apart atom by atom, only to hurl them across the planet in a grotesque, glowing downpour. The horror show begins with WASP-76b's extreme tidal locking. Like many close-orbiting exoplanets, one side perpetually faces its star, basking in temperatures that soar beyond 2,400 degrees Celsius, hot enough to vaporize iron, titanium, and even rock. But the real nightmare unfolds on the night side, where temperatures plummet to a still scorching 1,400 degrees. Here, the vaporized metals carried by supersonic winds from the dayside finally cool just enough to condense into droplets. The result, a perpetual hellish rain of liquid iron falling through skies choked with metallic mist. What makes this planet even weirder is its atmospheric circulation. Most tidally locked worlds have a day-night cycle where air moves in predictable patterns, but WASP-76b's atmosphere behaves more like a cosmic forge. Daytime heating creates winds screaming at over 18,000 kilometers per hour, tearing across the terminator, the line between light and dark, with enough force to keep the iron suspended until it reaches the colder night side. There, the metal cools just enough to form eerie, glowing droplets that plummet toward the surface. Some scientists speculate the night side might have vast iron lagoons, pools of molten metal gathering in low-lying areas, though no one knows for sure if the planet even has a solid surface to catch them. The strangest part, WASP-76b's rain might not even reach the ground. Its immense gravity, 6 times stronger than Jupiter's, could mean the iron vaporizes again before hitting anything solid, creating a surreal cycle of evaporation and condensation that turns the entire planet into a broiling, self-sustaining metal refinery. This isn't just a planet, it's a laboratory for extreme physics, a place where the laws of chemistry and fluid dynamics twist into something unrecognizable. Discovering WASP-76b forced astronomers to confront how little we understand about atmospheric processes under such brutal conditions. It's a world where the familiar concept of weather is replaced by something out of a blacksmith's nightmare, a perpetual metallic monsoon raging in the darkness of space. Most planets take their time, leisurely circling their stars over days, months, or even years. But PSRJ 1719-1438b scoffs at such cosmic complacency. It's the universe's ultimate speed demon, completing a full orbit in just 2.2 hours. That's right, a year here passes in less time than it takes to watch a movie, with this planet hurtling through space at an almost incomprehensible 1.4 million miles per hour. If Earth moved that fast, we'd zip around the Sun in under a week. But PSRJ 1719-1438b isn't just fast, it's a survivor, a cosmic phoenix that endured one of the most violent events in the universe and emerged transformed. This planet's story begins with catastrophe. It once orbited a massive star, one that eventually exploded in a supernova so powerful it should have vaporized any nearby worlds. But against all odds, this planet clung to existence not as the gas giant it likely once was, but as the stellar equivalent of a crushed diamond. The supernova's blast compressed its remains into a dense, carbon-rich core, stripping away its atmosphere and leaving behind what scientists suspect is essentially a planet-sized jewel. Today, it circles the corpse of its former star, a pulsar, a rapidly spinning neutron star that beams radiation like a cosmic lighthouse with such precision you could set your watch by it. The pulsar's gravity grips the planet with a vice-like hold, whipping it around at breakneck speeds. Imagine standing on its surface if you could survive the crushing gravity and lethal radiation, and seeing the pulsar loom overhead, a seething, spinning remnant of stellar fury. The sky would pulse with rhythmic flashes of light as the neutron star's beams sweep across the landscape like a celestial strobe, bathing the planet in waves of deadly energy. And that landscape, it might be unlike anything in our solar system, with pressures so intense they turn carbon into crystalline structures. PSRJ 1719-1438b could be littered with mountains of diamond, their facets glinting in the pulsar's eerie glow. Yet for all its dazzling extremes, this planet isn't just a cosmic oddity, it's a Rosetta Stone for understanding stellar violence. Its existence proves that planets can endure supernova, evolving into bizarre new forms under conditions we once thought impossible. And it raises tantalizing questions. How many other diamond worlds are out there, forged in the heart of dying stars? Could pulsar planets, bathed in radiation and sculpted by gravity, harbor even stranger secrets? The universe loves nothing more than to surprise us, and PSRJ 1719-1438b is a blazing reminder that even in destruction, new wonders are born. Deep in the heart of a globular cluster called Messier 4, where stars crowd together like fireflies in a jar, drifts a relic from the dawn of time, PSRB 1620-26b. At 12.7 billion years old, this ancient world has witnessed nearly the entire history of the universe itself. Born when the cosmos was just a toddler, barely a billion years old, it's the ultimate cosmic elder, a planet that predates our Sun by 8 billion years and has survived cataclysms that would obliterate most solar systems. What makes this planet so extraordinary isn't just its age, but where it calls home. A binary star system consisting of a pulsar and a white dwarf locked in a slow gravitational waltz. Most planets orbit single stars, but PSRB 1620-26b dances with two stellar corpses, remnants of violent stellar deaths that should have ripped any nearby worlds to shreds. Yet here it remains, a grizzled survivor of cosmic chaos, silently orbiting the ghosts of its former suns. The planet's very existence rewrites the story of how and when planets form. Conventional wisdom suggested that heavy elements like carbon and silicon, essential building blocks for rocky worlds, were too scarce in the early universe to create planets this old. Yet PSRB 1620-26b defies that logic, proving that the universe got creative with planet making far earlier than we ever imagined. Its composition remains a mystery, but astronomers suspect it's a gas giant, forged in a time when the first stars were still seeding the cosmos with the raw materials for new worlds. Living in a globular cluster adds another layer of strangeness. These densely packed stellar cities are notorious for their gravitational mayhem, with stars constantly buzzing past one another like bees in a hive. For a planet to survive here for billions of years without being flung into the void is nothing short of miraculous. It suggests PSRB 1620-26b might have migrated inward, nestling close to its binary hosts where their combined gravity shielded it from the cluster's relentless tug of war. But the real treasure lies in what this planet teaches us about resilience. It's endured supernova, stellar collisions, and the slow death of its original star, only to end up orbiting the stellar ashes. If planets could tell stories, this one would speak of an era when the universe was young, wild, and untamed, a time before Earth, before the Milky Way's spiral arms fully formed, when the first building blocks of life were still scattered across the void. Finding PSRB 1620-26b was like stumbling upon a fossil from the cosmic dark ages. Its longevity hints that planets might be far more common in the ancient universe than we ever dreamed, lurking in the shadows of time, waiting to tell their tales. And as we peer deeper into the past, who knows what other primordial worlds we'll find, each one another piece of the puzzle, each one rewriting the history of everything we thought we knew. In a cosmic display of celestial extremes, Kepler 70b and Kepler 70c take the concept of a hot world to apocalyptic new heights. These twin planets, each roughly the size of Earth, orbit their dying star so close that a single year passes in less than 6 hours on Kepler-70b and just over 8 on Kepler-70c. Imagine standing on either surface if you could, and watching your star swallow half the sky, its searing light blotting out the entire horizon as temperatures exceed 7,000 degrees Celsius. At that heat, rock doesn't just melt, it becomes a shimmering, reflective liquid, turning these worlds into what scientists suspect are literal mirrors made of lava. The most shocking detail: these planets shouldn't exist. Their host star, Kepler-70, is a subdwarf B star, the exposed, helium-burning core of what was once a sun-like giant. When it expanded into a red giant billions of years ago, its outer layers engulfed any nearby planets. Yet Kepler-70b and C somehow survived, likely as the skeletal remains of gas giants whose atmospheres were boiled away, leaving behind dense, metallic cores that now skitter across the face of their star like embers on a forge. Their orbits are so absurdly tight that if you placed them in our solar system, both would fit neatly inside the Sun's own circumference with room to spare. What does this mean for the planets themselves? Their surfaces, if they have defined surfaces at all, are almost certainly oceans of liquid rock, constantly churned by tidal forces so extreme they generate planetary-scale waves. The sheer heat radiating from their star would vaporize most metals into glowing hazes, possibly creating reflective layers of metallic vapor that act like funhouse mirrors, bending and distorting the already hellish light. Some theories suggest their daysides might be smooth as glass, polished by the relentless stellar wind, while the night sides could be a jagged wasteland of rapidly cooling magma, fracturing and reforming in endless cycles. But the real mystery is how they've avoided destruction. Stars like Kepler-70 typically shed their outer layers violently, generating waves of radiation that push planets outward. Yet these two worlds cling impossibly close, defying physics just enough to endure. One provocative theory suggests they might not be original planets at all, rather, the remnants of a single, larger world that was torn apart by the star's gravity, its fragments recongealing into these molten survivors. Kepler-70b and C are more than just scorched oddities. They're time capsules from a stellar apocalypse. Studying them offers clues about the fate awaiting planets in our own solar system when the sun swells into a red giant. They prove that even in the face of annihilation, some worlds refuse to vanish completely, instead transforming into something entirely new, blazing trails of liquid light across the cosmos. Among the countless worlds orbiting stars, there exists a different breed of planet, one that answers to no sun, bound by no orbit, wandering the cosmic void like a ghost in the night. Meet CFBD Sir 2149-0403, a rogue planet untethered from any star, drifting through the darkness of interstellar space with only the faintest glow of its own fading heat to betray its presence. This isn't just a planet without a home. It's a celestial outlaw, flung from its birthplace by gravitational chaos, or perhaps born in the isolation of a failed star-forming cloud. Unlike the orderly worlds of our solar system, CFBD Sir 2149-0403 is a free agent roaming the galaxy at its own pace, untroubled by the pull of a parent star. The temperature on its surface hovers around 400 degrees Celsius, warm enough to glow dimly in infrared, but cold enough that any lingering atmosphere would have frozen solid, leaving behind a desolate, airless wasteland. How does a planet end up exiled like this? The most likely explanation is violence. In the crowded nurseries of young star systems, gravitational tugs of war between massive planets can eject smaller siblings like cosmic slingshots, hurling them into the abyss at speeds high enough to escape their star's grasp forever. Alternatively, rogue planets might form directly from collapsing gas clouds too small to ignite into stars' stellar misfits doomed to wander from birth. Observations suggest there could be billions, even trillions of these nomads adrift in our galaxy alone, invisible to all but the most sensitive telescopes. Yet CFBD SIR 2149-0403 is special. It's one of the few rogue planets close enough, just 130 light-years away, for astronomers to study in detail. Its infrared signature reveals hints of methane and water vapor in what might be a thin, residual atmosphere, clinging to the planet like the last whispers of a lost world. Some theories even suggest that rogue planets could harbor subterranean oceans, heated by internal radioactivity, offering hypothetical refuges for life in the eternal night of interstellar space. The discovery of such worlds forces us to reconsider what it means to be a planet. If a world never orbits a star, does it still count? And what does their existence tell us about the turbulent early years of planetary systems, where gravitational pinball routinely ejects worlds into the void? CFBD SIR 2149-0403 is more than just a cosmic curiosity. It's a glimpse into the chaos of planetary formation, proof that for every stable system like ours, countless others have been torn apart, their lost children still drifting silently through the dark. And if rogue planets are as common as astronomers suspect, they could rewrite the rules of habitability. Far from the warmth of stars, these nomads might rely on dark matter annihilation, tidal heating, or the slow decay of radioactive elements to generate heat, turning what we think of as frozen wastelands into potential havens for exotic forms of life. The universe, it seems, has a way of making even the loneliest places stranger than we imagined. GJ1214b might just be the most perplexing water world ever discovered, a planet where the very air is thick with steam and the surface could be an endless global ocean. Located just 40 light-years away in the constellation Ophiuchus, this mysterious world defies easy classification. It's larger than Earth but smaller than Neptune, placing it in the enigmatic category of mini-Neptunes, planets typically thought to be shrouded in thick, gaseous atmospheres. Yet GJ1214b is anything but typical. Its density suggests something far stranger, a planet soaked in water with an atmosphere so humid it might resemble a planetary-scale sauna. The first clue to its aquatic nature comes from its eerily low density. While Earth is mostly rock and metal, GJ1214b's mass and size imply a composition richer in lighter elements, likely vast quantities of water, along with hydrogen and helium. But here's where it gets fascinating. Unlike our ocean-covered Earth, where water sits atop a rocky crust, this planet's structure could be far more extreme. Scientists speculate it might have a relatively small rocky core, drowned beneath an ocean so deep it could extend hundreds or even thousands of kilometers down, transitioning under immense pressure from liquid water to exotic high-pressure ices like ice Roman 7, a crystalline form of water denser than rock. Then there's the atmosphere, a stifling, opaque blanket that has frustrated astronomers' attempts to peer beneath it. Observations show it's likely dominated by water vapor, possibly mixed with hazes of photochemical smog, creating a permanent planet-wide fog. Some models even suggest the upper layers could host clouds made not of water droplets, but of salts or other exotic condensates, swirling in a mist so thick it obscures any view of the ocean below. The big question, of course, is whether this water world could harbor life. At first glance, GJ1214b seems tantalizingly promising. Liquid water is a key ingredient for life as we know it, and a global ocean could provide a stable environment for chemical reactions to unfold over billions of years. But the reality is far more complicated. The planet's proximity to its dim red dwarf star means it's likely tidally locked, with one side perpetually scorched and the other frozen in darkness. Even if a liquid ocean exists, the extreme pressures and possible lack of mineral-rich rock-water interfaces could make the chemistry of life difficult to sustain. Yet GJ1214b remains a prime target for future study precisely because it challenges our assumptions. Is it a steamy, high-pressure version of Earth or a waterlogged gas dwarf with no solid surface at all? The answer could reshape how we define habitable zones and what kinds of worlds might host life. With next-generation telescopes like the James Webb Space Telescope probing its atmosphere for molecular clues, we may soon learn whether this enigmatic planet is a cautionary tale or a beacon of possibility in our search for other ocean worlds. One thing is certain, in the cosmic menagerie of strange planets, GJ1214b stands out as a world where the familiar becomes alien, and the very idea of an ocean takes on new, unimaginable forms. Gliese 436b is the universe's paradox, a world where ice refuses to melt even as it burns. This Neptune-sized planet, 33 light-years away in the constellation Leo, defies every expectation we have about the behavior of matter under extreme conditions. Its surface is a surreal landscape of scorching hot ice, a form of water so compressed by the planet's immense gravity that it remains solid at temperatures hot enough to vaporize lead. Imagine an iceberg that doesn't just survive 800 degrees Fahrenheit but thrives in it, locked in a crystalline embrace by pressures thousands of times stronger than Earth's deepest ocean trenches. How is this possible? The answer lies in the bizarre physics of exotic ice. On Earth, ice exists in familiar hexagonal crystals we call ice 1H. But under the crushing grip of Gliese 436b's gravity, water molecules are squeezed into tighter, more efficient arrangements. Structures like Ice 7 or Ice 10, where the molecules pack so densely they resist melting even under blistering heat. This isn't the ice of glaciers or snowflakes. It's a super-dense alien lattice forged in the heart of pressure cookers we can barely replicate in labs. Some scientists speculate the planet's core might be encased in a mantle of this fiery ice, a slushy, semi-solid layer that behaves more like hot plastic than anything we'd recognize. But the strangeness doesn't stop there. Gliese 436b is slowly evaporating, its atmosphere bleeding into space like a comet's tail. The planet orbits so close to its dim red dwarf star, 30 times nearer than Mercury is to our Sun, that stellar radiation strips away its hydrogen layer atom by atom. Observations reveal a vast, shimmering plume of gas trailing behind the planet, a cosmic wake stretching at least 10 million miles. This isn't a gentle leak, it's a planetary hemorrhage, with the planet losing an estimated 1,000 tons of hydrogen every second. At that rate, it could shed its entire atmosphere in a cosmic blink, leaving behind nothing but a scorched, icy core. What's most unsettling is how this world resists categorization. It's too massive to be a rocky super-Earth, yet its density suggests it's not a standard gas giant either. The prevailing theory is that Gliese 436b started life as a Neptune-like planet, only to have its outer layers blasted away over billions of years, exposing its exotic, ice-rich interior. That would make it a cosmic onion, its layers peeled back by relentless stellar winds to reveal a heart of burning ice. Yet for all its violence, this planet might hold clues to the fate of other worlds orbiting volatile stars. Its slow-motion destruction offers a preview of what could happen to planets in similar orbits, a laboratory for studying atmospheric escape in real time. And that tale of evaporating hydrogen, it's a beacon for astronomers, a signpost pointing to the invisible forces shaping planets beyond our solar system. Gliese 436b doesn't just challenge our understanding of ice, it rewrites the rules of planetary survival under fire. From a distance, HD 189733b looks almost serene, a deep, tranquil blue reminiscent of Earth's oceans seen from space. But this is no watery paradise. That stunning cobalt hue comes from something far more sinister. A roiling atmosphere saturated with silicate particles, where winds tear across the planet at 5,400 miles per hour, fast enough to outpace a rifle bullet 7 times over. Welcome to the Hyperwind planet, a place where the very idea of weather becomes a nightmare. The planet's color hints at its chaos. Unlike Earth's blue, which comes from sunlight scattering off water, HD 189733b's azure glow is the result of its violent, glass-laden skies. High-altitude silicate clouds, tiny particles of vaporized rock, absorb red light and scatter blue, painting the entire planet in this eerie shade. But these aren't gentle, drifting clouds. The planet's tidally locked rotation, with one side forever facing its star and the other shrouded in darkness, creates a temperature gradient so extreme it fuels perpetual supersonic storms. On the day side, temperatures soar to 930 degrees Celsius, hot enough to melt lead and vaporize rock into a shimmering mist. Meanwhile, the night side plunges to a comparatively frigid 650 degrees, creating a pressure difference that whips the atmosphere into a frenzy. The result, winds that don't just howl, they scream. These aren't the leisurely jet streams of Earth, but a relentless, planet-spanning tempest that carries molten glass sideways in stinging, horizontal barrages. Imagine standing on this world, if you could, and being sandblasted by a storm of superheated razor shards, each one moving faster than a spacecraft re-entering Earth's atmosphere. The glass doesn't fall like rain. It flies like shrapnel, carried on gusts so powerful they could strip flesh from bone in milliseconds. What makes HD 189733b even stranger is how these winds shape its climate. Unlike Earth, where weather systems swirl and evolve, this planet's atmosphere operates like a single, monstrous engine. Dayside heating generates a convection loop that drags scorching air toward the night side, where it cools and plunges back toward the surface, only to be reheated and launched again in an endless, violent cycle. Some models suggest the winds might even be fast enough to redistribute heat across the planet almost evenly, preventing the night side from cooling as much as it otherwise would. Yet for all its fury, this planet offers astronomers a rare opportunity. Its atmosphere is so extended and so violently mixed that it's one of the easiest gas giants to study outside our solar system. Observations have detected water vapor, carbon dioxide, and even methane in its air, though any hint of life is laughable in such a maelstrom. Instead, HD 189733b serves as a laboratory for extreme physics, showing us how atmospheres behave under conditions we could never replicate on Earth. The lesson here is clear: beauty in space often masks brutality. That soothing blue orb isn't a haven, it's a furnace wrapped in a hurricane where the sky itself is a weapon. And as we discover more worlds like it, we're reminded that the universe doesn't just create planets. It forges monsters. Among the pantheon of strange worlds, one stands out not for extreme heat or bizarre composition, but for sheer cosmic spectacle, J1407b. This young gas giant, located about 430 light-years away in the constellation Centaurus, makes Saturn's iconic rings look like child's play. Imagine a ring system so vast it would dominate Earth's sky, stretching nearly 120 million kilometers wide, 200 times larger than Saturn's. If J1407b replaced Saturn in our solar system, its rings would outshine the full moon, casting eerie shadows across our planet and turning every night into a celestial light show. But these aren't just oversized rings, they're a dynamic, evolving construction site for moons. Within the swirling disks of dust and ice, astronomers have detected gaps and clumps that suggest newborn moons are actively forming, their gravity carving paths like cosmic bulldozers. Some of these moonlets could be as large as Mars, growing with each passing orbit as they sweep up material from the disk. This gives scientists an unprecedented glimpse into how satellites are born, a process we've only theorized about until now. On Earth, we see the finished products, moon systems like ours, frozen in time. But J1407b is caught in the act, its rings a live laboratory for planetary formation. The scale of this system defies belief. The outer edges of its rings are so far from the planet that they take nearly 3 Earth years to complete a single rotation. And unlike Saturn's relatively flat rings, J1407b's disk is warped, with sections tilted at odd angles, suggesting past collisions or the gravitational influence of unseen companion planets. The rings themselves are likely made of dust and ice, but their exact composition remains a mystery. Some researchers speculate they could contain exotic materials like carbon-rich compounds, making them darker and more complex than anything in our solar system. What's truly astonishing is how temporary this spectacle might be. At just 16 million years old, J1407b is a cosmic toddler, and its sprawling rings won't last forever. Over time, the same forces creating moons will also destroy the disk, as moonlets grow large enough to destabilize the delicate balance of the ring system. Within a few million years, a blink in astronomical terms, this breathtaking display could vanish, leaving behind a more conventional gas giant with a retinue of mature moons. For astronomers, J1407b is a rare opportunity to study planetary evolution in real time. It challenges our assumptions about how ring systems form and decay, offering clues about the early history of our own solar system. And it raises tantalizing questions. Could Jupiter or Saturn once have had rings this magnificent? Are there other young giants out there, hidden in the depths of space, still wearing their colossal rings like cosmic crowns? One thing's certain: the universe has a flair for drama, and J1407b is its most dazzling stage yet. If you think Earth feels solid under your feet, Kepler 131c and Kepler 10c would put our planet to shame. These ultra-dense super-Earths are the cosmic equivalent of Anvil's worlds, so packed with heavy elements they defy everything we thought we knew about how rocky planets form. Kepler 131c, for instance, is nearly 2.5 times Earth size but contains over 7 times more mass, making it denser than iron. That means if you could scoop up a handful of its surface material, it would weigh as much as a bowling ball. Even more baffling is Kepler 10c, initially nicknamed the Mega-Earth for its startling density, so extreme that astronomers first doubted whether such a massive rocky world could even exist. What makes these planets such cosmic oddities? The answer lies in their composition. Most super-Earths we've discovered are either gassy mini-Neptunes or water-rich worlds with thick atmospheres. But Kepler 131c and Kepler 10c are different. They are almost entirely rock and metal, compressed to degrees we've never seen before. Kepler 10c's density, in particular, suggests it could be up to 20% iron, a proportion that would require a planetary formation process far more extreme than anything in our solar system. Some scientists speculate it might be the stripped core of a failed gas giant, its atmosphere blasted away by stellar radiation over billions of years. Others propose these worlds formed in regions where the protoplanetary disk was unusually rich in heavy elements, creating planets that are more metal than stone. But here's the real puzzle. According to conventional models, planets this massive shouldn't be able to stay rocky. Once a world grows beyond about 10 Earth masses, gravity typically pulls in so much hydrogen and helium that it becomes a gas giant. Yet Kepler 10c weighs in at 17 Earth masses and somehow resisted that fate. One theory suggests its primordial disk might have been starved of light gases, forcing it to build itself almost entirely from dust and metal. Another idea is that it formed much farther from its star, where temperatures were cold enough for rocky materials to dominate before migrating inward to its current orbit. The implications are staggering. If planets can grow this massive and remain rocky, it means the line between terrestrial worlds and gas giants is blurrier than we ever imagined. It also raises tantalizing questions about their geology. Under such intense pressure, their interiors could host exotic forms of rock and metal we've never seen. crystalline structures deformed by gravity into bizarre configurations, or even layers of super-compressed minerals that behave more like liquids than solids. Kepler 131c and Kepler 10c aren't just planetary curiosities, they're cosmic rebels, rewriting the rules of what's possible. Their existence forces us to confront gaps in our understanding of planetary formation, proving that the universe has more than one way to build a world. And as we discover more of these ultra-dense anomalies, we're left wondering, are they rare flukes or just the first examples of a whole new class of planets waiting to be found? Among all the strange worlds we've encountered, few feel as cinematic as Kepler 16b, a real-life Tatooine where two suns grace the horizon. This gas giant, orbiting a binary star system 200 light-years away, turns science fiction into reality with its mesmerizing double sunsets. Picture standing on a hypothetical moon around this planet, watching twin shadows stretch across the landscape as the stars dip below the skyline in perfect tandem. One an orange-hued K-dwarf, the other a smaller, redder M-dwarf, each casting its own hue across the clouds. But how does a planet survive the gravitational tug of war between two stars? Most binary systems shred planet-forming disks long before worlds can coalesce, yet Kepler 16b orbits in a Goldilocks zone of stability. Its path traces a wide circle around both stars at once, a configuration astronomers call a circumbinary orbit. The key lies in distance. Kepler 16b stays far enough out that the star's chaotic dance doesn't fling it into the void. Think of it like a cosmic hula hoop. Swing two weights tied to a string in circles, and there's a sweet spot where a third object can rotate around both without being yanked off course. The planet's formation is even more mind-bending. Conventional wisdom suggested binary stars would scatter protoplanetary material before it could clump together. Yet Kepler 16b likely assembled in the outskirts of this system, where the star's gravitational influence was weaker before migrating inward. Its existence proves that planets can emerge from the debris disks of binary systems, a revelation that's reshaped our search for habitable worlds, as binary stars make up over half the stellar population in our galaxy. What's most striking is the rhythm of its orbit. Every 229 days, Kepler 16b completes a loop around its twin suns, which themselves whirl around each other every 41 days. That means the star's own orbital motion subtly distorts the planet's path, creating a wobble that would make our solar system's neat ellipses look dull by comparison. The planet doesn't just orbit two stars, it navigates a labyrinth of shifting gravity, adjusting in real time to their dance. Kepler 16b isn't just a novelty, it's a celestial Rosetta Stone. By studying its orbit, astronomers have unlocked secrets about how planets form in the most chaotic environments. And with every new circumbinary world discovered, now numbering in the dozens, we're forced to reconsider where life might take root. Could a moon around a planet like this, bathed in the light of two suns, hold liquid water? The universe keeps offering up worlds that stretch our imagination, and Kepler 16b stands as proof that sometimes truth really is stranger than fiction. K220-2b isn't just a planet, it's a cosmic hourglass, its very existence measured in vanishing grains of dust. Located 800 light-years away in the constellation Leo, this bizarre world is evaporating before our eyes, leaving behind a tail of debris stretching over 10 million miles. Imagine a comet, but instead of ice vaporizing under the sun's heat, this is an entire planet unraveling, its atmosphere torn away atom by atom as it orbits perilously close to a violent red dwarf star. The numbers alone are staggering. K220-2b completes a full orbit every 9 hours, its surface scorched to temperatures exceeding 900 degrees Celsius. At that proximity, the star's radiation bombards the planet like a blast furnace, heating its rocky surface until it glows, but the real drama happens in the atmosphere. Unlike gas giants with deep gravity wells to hold onto their air, K222b is a lightweight, likely a super-Earth or sub-Neptune, with just enough gravity to loosely tether its gases. As the star's relentless fury excites those molecules, they reach escape velocity, streaming into space like steam from a boiling kettle. What makes this planet truly unique is the trail it leaves behind. Observations reveal a vast, comet-like tail of dust and vapor stretching far beyond the planet itself. This isn't just random debris, it's the literal remains of K222b's outer layers, a forensic record of its dissolution. The dust likely forms when vaporized rock and metals in the escaping atmosphere cool and condense into microscopic particles, creating a glittering, doomed halo around the planet. Some estimates suggest it's losing over 10,000 tons of material every second, enough to strip an Earth-sized planet bare in a mere 100 million years. Yet K222b's slow-motion destruction isn't just a spectacle, it's a preview. Across the galaxy, countless planets orbiting close to their stars face similar fates. Red dwarfs, the most common stars in the universe, are notoriously volatile, prone to flares that can scorch nearby worlds. Over billions of years, these stars gradually calm, but by then, planets like K222b may be little more than skeletal cores, their atmospheres long since blasted away. This evaporation process, known as hydrodynamic escape, could explain why so few mid-sized planets are found in tight orbits around such stars they've been reduced to barren husks. The eerie beauty of K222b is that it lets us watch this apocalypse in real time. Most planetary evolution happens too slowly for human observation, but here the timescales are compressed enough to witness change within years, not eons. Already, astronomers have noted fluctuations in the dust tail's brightness, hinting at bursts of evaporation triggered by stellar flares. It's as if the planet is gasping for air between each searing blast from its star. What remains when the escape is complete? The end product might resemble Mercury, a dense, airless rock, its surface cratered and baked by eons of exposure. But even that assumes K222b survives at all. Some models suggest the entire planet could disintegrate, its core torn apart by tidal forces once its atmosphere no longer cushions the star's gravitational pull. If so, that glittering tail might one day be all that's left, a ghostly smear of dust where a world once orbited. K222b forces us to confront the impermanence of planets. In the grand timeline of the universe, even worlds are fleeting, their fates dictated by the stars they orbit. Yet in its demise, this shrinking planet offers a gift, a chance to unravel the secrets of atmospheric loss, one escaping molecule at a time. Every speck of dust in its wake tells a story, not just of destruction, but of the incredible forces shaping planetary systems across the cosmos. HD 80606b doesn't just have seasons, it has planetary whiplash. This gas giant, 200 light-years away in the constellation Ursa Major, holds the record for the most extreme orbit ever discovered. A dizzying ellipse so stretched that its distance from its star ranges from an almost touching 3 million miles to a far-flung 83 million miles over the course of its 111-day year. That's like swapping Mercury's orbit with Mars's and back again every 4 months. The result, a world where temperatures don't just rise or fall. They explode, swinging from 980 degrees Fahrenheit to 2,240 in a matter of hours. Imagine standing on this planet, if its crushing gravity and searing winds didn't obliterate you first, and watching the sky transform at terrifying speed. As HD 80606b plunges toward its star, its atmosphere reacts like gasoline tossed on a bonfire. Infrared observations reveal that its sunward side heats up so violently it glows like molten iron, triggering shockwaves of supersonic storms that race across the planet at over 11,000 miles per hour. These aren't gentle breezes, they're atmospheric tsunamis, generated by temperature gradients so steep they make Earth's fiercest hurricanes look like lazy summer gusts. But the real chaos begins when the planet reaches its closest approach. Tidal forces from the star's gravity stretch and compress the planet's interior, pumping energy into its already frenzied weather systems. The result is a feedback loop of storms as the dayside boils superheated air rockets toward the cooler nightside, only to cool, sink, and rush back in a self-perpetuating cycle of violence. Some models suggest the planet might actually pulsate slightly under the strain, its outer layers swelling and contracting like a cosmic heartbeat. Then comes the backswing. As HD 80606b hurtles back toward the outer reaches of its orbit, its atmosphere undergoes a brutal deep freeze. The same storms that raged during its scorching close pass now funnel heat away from the core, triggering a rapid cool-down that transforms vaporized metals and silicates into glittering, razor-edged clouds. These tempests don't fade, they mutate, twisting into new configurations as the planet's rotation and orbit interact in a gravitational tug-of-war, the most baffling part. This world shouldn't exist. Orbits this extreme are usually unstable, with planets either crashing into their stars or being flung into the void within a few million years. Yet HD 80606b has endured for billions, possibly thanks to the gravitational influence of a distant binary companion star that nudges it just enough to maintain its precarious dance. For astronomers, this planet is more than just a spectacle, it's a masterclass in atmospheric physics. By studying how its air responds to such violent temperature swings, we're learning how gas giants evolve under conditions far beyond anything in our solar system. And it raises a tantalizing question. If a planet can weather these extremes, what other atmospheric nightmares might be lurking in the cosmos? HD 80606b doesn't just push the envelope, it shreds it, proving that when it comes to weather, the universe's creativity knows no bounds. Among the gallery of bizarre exoplanets, JJ504b stands out with a color palette that seems plucked from a dream, a luminous, bubblegum pink gas giant drifting far from its star. This youthful world, just 160 light-years away in the constellation Virgo, glows with the residual heat of its violent birth, radiating a soft magenta hue that defies the muted tones of most gas giants we know. If you could float near this planet, its rosy glow would bathe everything in an otherworldly light, like standing inside a neon sign. What gives JJ504b its striking color? The answer lies in its infancy. At just 160 million years old, 30 times younger than Earth, this planet is still cooling from the intense heat of its formation. Its atmosphere churns with turbulent storms and roiling clouds, but unlike Jupiter's familiar ammonia-rich bands, JJ504b's outer layers are dominated by exotic compounds like methane and water vapor. These molecules absorb certain wavelengths of light while scattering others, filtering its starlight into that surreal pink glow. Infrared observations reveal even deeper strangeness. The planet emits far more heat than it receives from its star, a lingering thermal fingerprint of the gravitational energy that shaped it. Yet JJ504b's most puzzling feature isn't its color. It's where it orbits. This planet circles its sun-like star at nearly 9 times Pluto's average distance, a vast gulf that shouldn't exist according to standard gas giant formation models. Core accretion theory, which explains how planets like Jupiter form, suggests gas giants need to condense relatively close to their stars, where the protoplanetary disk is dense enough to supply material for rapid growth. But JJ504b defies that logic, lingering in the frigid outskirts where the disk would have been too sparse for traditional planet building. Some scientists propose it might have formed via gravitational instability, a process where a collapsing pocket of gas and dust spontaneously fragments into a planet without the slow accumulation of a solid core. Others speculate it was born closer in and then flung outward by gravitational interactions, though no obvious perturbers exist in the system today. The implications ripple beyond this one pink oddity. GJ504b forces us to reconsider how planetary systems take shape, especially around young stars. Its wide orbit suggests planetary formation might be more chaotic and varied than we thought, with some worlds assembling in ways that leave them forever estranged from their stars. And then there's the question of its atmosphere. Unlike mature gas giants whose compositions are shaped by billions of years of chemical evolution, GJ504b offers a snapshot of a primordial atmosphere, one that could reveal what Jupiter's skies looked like in the solar system's fiery youth. Future observations might uncover even more surprises. The planet's pink tint could hint at unknown photochemical processes unfolding in its upper layers, or even trace compounds forged in the extreme pressures of its interior. Each new study peels back another layer of mystery, proving that even a planet as visually stunning as GJ504b hides its most profound secrets beneath that candy-colored glow. One thing's certain, in the cosmic art gallery, this world is the masterpiece that refuses to fit any frame. If HD 80606b is the poster child for orbital chaos, Kepler 50, 1b is the universe's answer to a cosmic marshmallow, a planet so light and fluffy, it defies the very definition of what a world should be. This super puff planet, nearly the size of Jupiter but with less than 1% of its mass, has a density lower than styrofoam. Picture a celestial body so insubstantial that if you could somehow place it in a cosmic bathtub, it would float effortlessly, bobbing like a rubber duck in zero gravity. The numbers alone are staggering. Kepler 50, 1b's atmosphere balloons outward to an almost cartoonish degree, stretching tens of thousands of kilometers into space so vast and diffuse that it blurs the line between planet and protoplanetary disk. Unlike the crushing pressures of gas giants like Jupiter, where gravity compresses hydrogen into metallic forms, this world's outer layers are more akin to spun sugar, a wispy shroud of hydrogen and helium held together by the faintest gravitational whisper. Its composition suggests an atmosphere dominated by lightweight gases, possibly mixed with methane or water vapor, but the real mystery is how such a fragile structure hasn't evaporated into the void. One leading theory points to youth Kepler 50. 1b is a cosmic toddler just 500 million years old, still cooling from its formation. Heat trapped in its interior might be inflating its atmosphere like a hot air balloon, counteracting gravity's attempts to compress it. Yet even that doesn't fully explain the planet's extreme puffiness. Some scientists speculate that its orbit plays a role. Nestled close to its star, the relentless stellar radiation could be pumping energy into the upper atmosphere, causing it to swell like bread dough in an oven. Others suggest the planet might be surrounded by vast rings or a swarm of moon-forming debris, their collective gravity subtly propping up the atmosphere. Then there's the question of escape. Planets this fluffy shouldn't last. At Kepler 50, 1b's low-density, atmospheric molecules should reach escape velocity with ease, bleeding into space like steam from a boiling kettle. Yet somehow the planet persists. One tantalizing possibility is that it's actively replenishing its atmosphere, perhaps through volcanic outgassing or the slow evaporation of icy material dredged up from its interior. Alternatively, its extended atmosphere might be so vast that even rapid loss would take billions of years to strip it bare, like a glacier melting grain by grain. What's undeniable is that Kepler 50, 1b challenges our understanding of planetary evolution. It's a living laboratory for testing how gas giants form and age, a place where the rules of physics stretch to their breaking point. And it's not alone. Its system hosts two other superpuff siblings, all orbiting the same star, suggesting this isn't a fluke but a genuine class of worlds waiting to be understood. The deeper we look, the more these cotton candy planets force us to rethink the boundaries of planetary science. They're reminders that the universe doesn't just build worlds, it experiments, crafting extremes that push our imagination to the limit. And somewhere out there, floating in the cosmic breeze, Kepler 50, 1b drifts like a whispered question, daring us to unravel its secrets. If you thought WASP 76b's iron rains were extreme, brace yourself for the stellar infernos of Kelt 9b and WASP 12b, two ultra-hot Jupiters so scorching they blur the line between planet and star. Kelt 9b, the hotter of the pair, boasts dayside temperatures soaring beyond 4,300 degrees Celsius hotter than the surface of some red dwarf stars. This isn't just a planet, it's a celestial forge where molecules are ripped apart atom by atom, creating an atmosphere more akin to the outer layers of a star than any world in our solar system. At these temperatures, even the sturdiest molecules surrender. Water vapor, carbon dioxide, even titanium oxide, all dissociate into their elemental components, leaving behind a broiling soup of ionized hydrogen, helium, and free-floating metal atoms. The extreme heat also warps the planet's shape, stretching its atmosphere outward like taffy under the star's gravitational pull. Hubble observations reveal Kelt 9b's atmosphere is so inflated it's actively escaping, trailing behind the planet like a comet's tail as it orbits its searing host every 36 hours. WASP 12b, meanwhile, offers a darker twist. While slightly cooler at 2,600 degrees, its proximity to its star creates a gravitational nightmare. Tidal forces have stretched the planet into an egg shape, while its carbon-rich atmosphere, thick with methane and carbon monoxide, absorbs over 94% of incoming starlight, turning it into one of the darkest known planets. But the real horror lies in its fate. WASP 12b is being devoured alive. The star's gravity strips away 300 billion tons of material every second, pulling the planet's outer layers into a swirling disk of debris. At this rate, astronomers estimate it has less than 10 million years left before complete disintegration, a cosmic snack unfolding in real time. What unites these worlds is their defiance of planetary norms. Their extreme heat triggers chemical reactions impossible elsewhere, like the formation of ionized calcium and iron rain that falls upward, drawn by magnetic fields into the star's grasp. They're also reshaping our understanding of atmospheric escape, showing how stars can erase planets not through collisions, but by slowly boiling them into oblivion. Yet for all their violence, Kelt 9b and WASP 12b are celestial goldmines. By studying their death throes, we're glimpsing the brutal physics governing planets orbiting too close to their suns, and perhaps predicting the fates of countless others. These aren't just scorched worlds, they're blazing textbooks rewriting the rules of planetary survival under fire. LTT 9779b is the universe's middle finger to planetary science, a world that by all rights should have vanished eons ago. Dubbed the impossible planet, this ultra-hot Neptune defies one of astronomy's most puzzling mysteries, the hot Neptune desert. This cosmic no-man's land refers to the eerie scarcity of planets sized between Earth and Jupiter orbiting scorchingly close to their stars. The math is brutal at such proximity. Stellar radiation should blast away the atmospheres of Neptune-sized worlds within a few million years, leaving behind nothing but barren cores. Yet LTT 9779b lounges in this forbidden zone, a gas-shrouded paradox circling its star every 19 hours at temperatures hot enough to melt platinum. The planet's defiance begins with its atmosphere, an unexpected cloak of gas that somehow clings to its frame despite the relentless stellar onslaught. Most hot Neptunes discovered before it were either stripped-down husks or in the process of evaporating, their atmospheres trailing behind them like comet tails. But LTT 9779b's air remains intact, a thick shroud of hydrogen and helium that refuses to surrender. Observations suggest its atmosphere might be unusually metal-rich, laden with sodium and potassium, which could act like a chemical sunscreen, absorbing and re-radiating enough heat to slow atmospheric escape. Another theory posits that the planet's core generates a potent magnetic field, creating an invisible shield that deflects the star's particle blasts and traps its atmosphere like a cosmic pressure cooker. Yet even these explanations feel insufficient. The planet's density hints at another layer of strangeness. It's far heavier than typical hot Neptune's, with a core potentially 28 times Earth's mass. That immense gravity might be the ultimate anchor, hoarding its atmosphere like a dragon guarding treasure. Or perhaps the planet is a recent arrival, violently shoved into its current orbit by a gravitational tug of war, buying it time before the star's radiation begins its slow demolition. What's undeniable is that LTT 9779b forces astronomers to rewrite the rules. Its existence suggests the hot Neptune desert might not be entirely barren, just selective, hiding worlds that have cracked the code of survival. Future studies could reveal whether it's a fluke or the first of a hidden population lurking in the data of past surveys. Until then, this impossible planet stands as a taunting enigma, a reminder that the universe's playbook is far from complete, and its outliers often hold the keys to the next revolution in understanding. Beyond the known worlds of our solar system, in the frigid blackness where sunlight is a distant memory, something massive may be lurking, an unseen gravitational puppeteer tugging at the orbits of distant objects. This is Planet 9, a hypothetical super-Earth up to 10 times the mass of our world, hiding so far from the Sun it would take 15,000 years to complete a single orbit. The evidence for its existence isn't a photograph or direct observation, but a trail of celestial breadcrumbs written in the peculiar paths of icy bodies drifting beyond Neptune. The story begins with the Kuiper Belt, a ring of frozen debris where dwarf planets like Sedna and Biden follow orbits tilted wildly out of alignment with the rest of the solar system. These objects don't just drift randomly, they're closest approaches to the Sun cluster in a way that suggests an invisible hand herding them. Mathematical models show the probability of this pattern occurring naturally is a mere 0.2%, leading astronomers to propose a massive, distant planet as the architect of this cosmic choreography. Its gravity would act like a shepherd's crook, nudging these objects into their strange, synchronized dances over billions of years. What makes Planet 9 so tantalizing is how it upends our understanding of the solar system's architecture. If it exists, it likely didn't form in place. Current theories suggest it might have been ejected during the solar system's chaotic infancy, only to be recaptured in a vast elliptical orbit. Alternatively, it could be a rogue planet snatched from another star during the Sun's birth cluster and adopted into our own family. Either scenario would rewrite planetary formation models, proving our cosmic neighborhood has more secrets than we ever imagined. The hunt for this phantom world is anything but easy. At an estimated distance of 600 astronomical units, 20 times farther than Neptune, Planet 9 would reflect so little sunlight it's effectively invisible to all but the most sensitive telescopes. Searchers using instruments like Subaru and the Vera Rubin Observatory scan for its faint infrared glow or telltale gravitational microlensing effects. Some researchers have even proposed detecting its hypothetical moons through radio emissions caused by charged particles interacting with its magnetic field. Yet skepticism remains. Critics argue the orbital anomalies might stem from observational bias or the collective gravity of smaller Kuiper Belt objects. Others suggest a primordial black hole could explain the gravitational disturbances without needing a planet at all. Until definitive proof emerges, Planet 9 exists in a limbo between discovery and myth, a celestial ghost story written in equations and gravitational whispers. Whether confirmed or debunked, the search itself has already reshaped astronomy. It's reminded us that even in our own backyard, the cosmos holds puzzles we've barely begun to solve. And if Planet 9 is real, It would be more than just another world. It would be a relic of the solar system's violent youth, a frozen giant waiting in the dark to tell its story. Until then, it remains the ultimate cosmic hide-and-seek champion, daring us to find it. Before we close this cosmic tour, let's rewind to where it all began. PSRB 1257+12b, a world that shouldn't exist, orbiting a star that shouldn't host planets. This unassuming pioneer, discovered in 1992, wasn't just the first confirmed exoplanet, it was a cosmic revolution wrapped in a paradox. Picture a planet circling a pulsar, the spinning corpse of a supernova so violent it should have annihilated any nearby worlds. Yet there it was, a survivor clinging to the ashes of stellar catastrophe, rewriting astronomy's rulebook overnight. The discovery was as improbable as the planet itself. Astronomers Alexander Wolskson and Dale Frail weren't even hunting for planets. They were studying the pulsar's radio pulses, hyper-precise flashes so regular they could set atomic clocks. But something was off. The pulses wobbled rhythmically, as if an invisible dancer tugged at the star. The culprit, not one, but 3 planets with PSRB 1257+12b as the innermost. The scientific community reeled. Conventional wisdom insisted planets couldn't form around pulsars. Their explosive birth should sterilize entire systems. Yet here was proof that nature had other plans. This wasn't just a planet, it was a Lazarus world resurrected from stellar Armageddon. The leading theory suggests it formed from the wreckage of the supernova itself. As the dying star exploded, debris might have collapsed into a disk around the pulsar, forging new worlds from the ashes of the old. Alternatively, the planets could be the shattered remains of a binary companion star, torn apart by the pulsar's gravity and reassembled into planetary orphans. Either scenario paints a picture of cosmic resilience, where destruction and creation dance hand in hand. PSRB 1257+12b's impact can't be overstated. Before its discovery, exoplanets were theoretical curiosities. Afterward, they became inevitabilities. The floodgates burst open, with astronomers racing to develop new detection methods, from radial velocity to transit photometry, each building on Wolskson and Frail's groundbreaking work. Today, we know of over 5,000 exoplanets, but this pulsar's companion remains one of the most enigmatic. Its very existence forces us to confront how little we understand about planetary formation's outer limits. What does it feel like to orbit a pulsar? The view would be both beautiful and lethal. The planet's sky would pulse with rhythmic strobes of radiation as the neutron star's beams sweep across its surface like a lighthouse from hell. Dayside temperatures might soar from trapped heat, while the night side freezes in perpetual shadow, a world of extremes sculpted by the pulsar's ruthless energy. And through it all, PSRB 1257+12b endures, a silent testament to the universe's boundless creativity. Its legacy lingers in every exoplanet discovered since. This unassuming pioneer proved that planets aren't rare accidents, they're cosmic constants, thriving in places we once deemed impossible. From diamond worlds to rogue nomads, the menagerie we've explored exists because one pulsar's pulse whispered a secret. The universe is stranger and far more wondrous than we ever dared to dream. The hunt for the universe's strangest worlds is only getting wilder, thanks to telescopes and technologies pushing the limits of what we can see. Imagine instruments so advanced they can spot the faint shadow of an exomoon drifting across a distant star, or detectors sensitive enough to catch the gravitational ripples from a hypothetical quark star, a cosmic oddity so dense it's made entirely of subatomic particles frozen in a state beyond neutronium. This isn't science fiction, it's the bleeding edge of astronomy, where every new tool peels back another layer of the impossible. Take the James Webb Space Telescope, for instance. Already, its infrared eyes have dissected the atmospheres of planets like never before, sniffing out molecules in alien skies with the precision of a cosmic chemist. But Webb is just the beginning. Upcoming missions like the European Space Agency's Pluto aim to discover thousands more exoplanets with a special focus on Earth like worlds orbiting Sun like stars. Though given the universe's track record, Earth-like could mean anything from hypervolcanic hellscapes to planets with oceans of liquid methane. Meanwhile, the Nancy Grace Roman Space Telescope, set to launch later this decade, will use microlensing to spot rogue planets drifting between stars, worlds without suns that might outnumber the stars themselves. Then there's the tantalizing hunt for ExoMoon's planetary satellites lurking in the habitable zones of gas giants. Think Pandora from Avatar, but real. Current methods rely on dips in starlight or gravitational tugs, but future observatories could directly image these moons, analyzing their atmospheres for signs of water or even biosignatures. One candidate, Kepler 1625 b, already hints at this possibility, with data suggesting a Neptune-sized moon orbiting a Jupiter-like planet. If confirmed, it would shatter our assumptions about where life could thrive. But the true frontiers lie beyond planets entirely. Theorists speculate about quark stars, objects even denser than neutron stars, where gravity crushes matter into a soup of quarks. These hypothetical monstrosities could explain anomalous cosmic explosions or act as dark matter anchors, warping spacetime in ways we've yet to imagine. And let's not forget the tantalizing possibility of Planet X, a hypothetical super-Earth lurking in our own solar system's outskirts, its gravity sculpting the orbits of distant Kuiper belt objects. The next decade promises revelations that'll make today's strangest planets seem quaint. With 30-meter-class ground telescopes like the Extremely Large Telescope coming online, we'll peer deeper into planetary atmospheres, untangling their chemistry in unprecedented detail. Meanwhile, projects like the Laser Interferometer Space Antenna LISA will listen for gravitational waves from colliding exotic objects, potentially unveiling entirely new classes of worlds. What's clear is this: the cosmos has only begun to show its hand. Every strange discovery rewrites the rules, proving that the universe's imagination far outstrips our own. And as our tools grow sharper, so too does the promise of finding worlds so bizarre, they'll force us to rethink what a planet even is. From diamond worlds that glitter with crystallized carbon to planets darker than the void itself, our journey through the cosmos has revealed worlds stranger than fiction. 55 Cancri taught us that planets can become cosmic jewelry boxes, while WASP 76b proved weather could mean sideways showers of molten iron. We've met rogue planets drifting like ghosts between stars, ancient survivors older than the sun itself, and hyper-puffed worlds with densities lighter than candy floss. Each one of these discoveries didn't just add to our catalog of exoplanets, they shattered the textbook definitions of what a planet could be. Think about what that means for our place in the universe. Not long ago, we assumed our solar system was the blueprint, planets neatly orbiting in stable, predictable paths. Now we know the cosmos thrives on chaos, crafting gas giants that orbit backward, planets with triple sunsets, and molten worlds where the very ground beneath your feet would be liquid mirror. These aren't exceptions, they're proof that the universe operates on a scale of creativity we're only beginning to grasp. Every oddball world forces us to rewrite the rules, turning planetary science into a living, evolving field where today's certainty is tomorrow's mystery. And the wildest part, this is just the beginning. For every planet we've discovered, thousands more lurk in the data, waiting for sharper telescopes or clever algorithms to tease them into view. What else is out there? A world where it rains sapphires, a planet with hexagonal oceans, or perhaps something so bizarre we lack the language to describe it. The tools we're building now, like the James Webb Space Telescope and upcoming ground-based observatories, promise to peel back even more layers of this cosmic onion, revealing realities that might make today's strangest finds seem tame. So stay curious, because the universe isn't just stranger than we imagine. It's stranger than we can imagine, and somewhere in that vast, uncharted dark, the next great planetary marvel is waiting, ready to defy expectations all over again. The only question is, when we find it, will we even believe what we're seeing?